If I asked a 3-year-old, what's 3? What would a 3-year-old tell me?
Their age?
Yeah, I'm 3. Are you 3? It's nice to meet you. I've always wanted to meet 3. No, I'm not 3. I'm 3 years old. Oh, okay. What does that mean? How many years is that?
1 more than 2.
Now then I'm going to ask you, what's 2?
1 more than 1.
And then I'm going to ask you what 1 is. What are you going to show me?
Like your 1 finger.
Aha. That's exactly it. What is 3? 3 is these many, right? And we all have different names for it, but it's these many. If I want to know what 3 is, I'm going to go out and I'm going to say, okay, I have 3 people in my family. There's me and my mate and my kid. Okay? That's how we count. We make a one-to-one correspondence with these many. And we don't even think about it, which is sort of miraculous. I mean, we have gotten to the point where we think about numbers without actually thinking about the things they represent. We can think about 3 without thinking about 3 what? Well, 3 what? The 3 doesn't exist by itself. It's these many or something. And the thing is that numbers in a very real way are a human construct. We made it up. To give you a really good example of what that means, when Europeans were sailing the globe for the first time, there are reports that one particular group of explorers landed on an island in the South Pacific, and they met a group of people. And that group of people, it turned out, had a counting system that only went up to 4. You had 1, and then 2, and then you had 1 more than 2, or you had 2 2s. And when they asked, well, what do you do with when you have more than that? They laughed. They said, what are you talking about more than that? If you're going to deal with more than that, you might as well count the hairs on my head. I mean, you think about the Romans, right? They did letters for numbers, but as far as I know, M was the biggest number they had, and M meant 1,000. And really didn't need to count much more than that in those days. And when they talk about Helen of Troy, the face that launched 1,000 ships, not talking about exactly 1,000 ships, like, okay, we got 999, but Peter is late again today. We got to wait for him. No, that's not what they meant. 1,000 ships was more than you could count. More, the sea was full of ships. And of course, we have a number for that too. We call it a bazillion or a gazillion or whatever it is you have to use. I mean, we talk about it. We have a word for more than you can count. It's just sort of a slang word, but we use it. And that's actually how our number system sort of developed. We had, positive integers for a while. And then they came up with rational numbers, which are numbers you could put in a ratio. So basically fractions, which later became, with the decimal system, later became decimals that terminate, right? And then you had irrational numbers. And irrational numbers, I mean, they came up in a number of different ways. One way was talking about circles, right? You could have a circle, and the distance, you could measure the distance around the circle, and you could measure the distance straight through the circle. And no matter how big or small the circle is, it turns out that if you make a ratio out of the distance around the circle and the distance through the circle, that number is always a little bit more than 3. It doesn't matter how big or small the circle gets, right? distance around is a little, divided by the distance through, is a little bit more than 3. How much more than 3? I can't tell you. It's immeasurable. It's, you know, I just cannot tell you. And that's why they developed a name for it. The number itself didn't exist, but they developed a name for it, and they called it pi, and it's equal to the circumference divided by the diameter. Okay, and it's a little more than 3, but I can't tell you exactly how much it is. If you measure straight across and you measure that to an exact number, then you can't tell me exactly how far around it is, and that's kind of strange. In one of Plato's dialogues, you know, where he talks about, he writes about what Socrates said. There's this whole thing about whether or not it's possible to draw a square with an area of 2. Okay, and it's an interesting conversation because the topic really has to do with whether or not people learn or whether they just remember from before they were born, whether before you were born, your soul actually knew absolutely everything. So that's actually the topic he's discussing, but he brings this up as his example. And basically, you know, you look at this and you say, okay, that's weird. You look at this and you say, okay, this is a square of 4, right? 1, 2, 3, 4. And the side length of this is 2. So in our words, 2 would be the square root of 4, because this is a square of 4, and the side of the square, which basically is the root, because that's all you need to draw it, is 2. This is a square of 1, and the root of that square is 1. But the thing is, how can you make this square smaller and smaller and smaller so that between 4 and 1, there is a square of 2, where there are exactly 2 squares inside? And of course, if you're just thinking in terms of putting squares like this, you can't do it. And in fact, if you're trying to think of, well, what would the length of a side be to create a square of 2? Well, the answer is there isn't one. I can't come up with a number that would make that happen. So what he wanted to know was, is there such a thing as a square of 2? And, you know, everybody that was standing around him said, no, I don't think so. I guess not, because I can't figure out how to do it. So then he did this. Right? He cut this one in half, and then he cut this one in half, and then he cut this one in half like this, and then he cut this one in half like this. And he said, okay, what do I have here? What's the area of this thing I just drew? And everybody had to admit that the area had to be 2. Why? Well, because there's a half and a half, which is 1, and a half, which is 1. And if you put them together, you have 2. And the thing is, he proved that you could have a square of 2, but he never went back and asked the question, how long is this? Because the ancient Greeks had absolutely no concept of irrational numbers. We now call this number something. We called it, you know, basically the square root of 2, because that's what it is. It's the length of the side of a square that gives you an area of 2. And then we made a squiggle for it, right? Because that's all our numbers really are when we write them. They're just squiggles that represent how many we're talking about. And this is what we wrote as our squiggle for the length of this line. This is the number that when you multiply it by itself gives you 2, or it is the length of the side of a square with an area of 2. Okay, so at some point you learned all of this. And you learned that there were whole numbers, and you learned that there were fractions or decimals, and you learned that there were irrational numbers, and then you learned that all of these together, and you say, okay, these are the real numbers. And that was all anybody ever told you. These are real numbers. The fact that we have a name for them means we're distinguishing them from something. So if those are the real numbers, the question becomes, what are the fake numbers? What happened was there were equations that looked like this, and we could find solutions for them. And then there were equations that looked like this, and we couldn't find solutions for them. And why was that? Because we were talking about a square with an area of -1. You say to yourself, well, okay, I'm sorry, but that just doesn't fit with my understanding of the universe. My guess is that today it's easier for you to imagine than it was years ago, because you've seen so many science fiction things, right? That if I draw squares that look like this, and then this, right? You can sort of imagine that if you get small enough and small enough, you get a little point here, which is essentially a square with no area at all. But I mean, after Alice in Wonderland and every science fiction movie you've ever seen where there's some other universe somewhere else that you can't see, or sort of Alice through the looking glass, if I'm looking at a mirror sideways here and Alice is here and she steps through the looking glass and then suddenly she's in an alternate universe, right? Well, it wouldn't be hard to imagine that somewhere on the other side of this, squares start getting bigger again, but their side lengths are negative numbers. Now, what am I asking you to do? I'm asking you to imagine this, because this doesn't exist in our universe at all. But so those are imaginary numbers. Okay. And what somebody did was say, okay, I'm going to imagine that there is a square with an area of -1, and it looks like this. The side length is this, okay? And that then allows me to do a whole lot of other things, including finding solutions to those equations I couldn't find solutions for. Those are imaginary numbers. And of course, you can do imaginary numbers by saying 2i, 3i. So now all of a sudden we can multiply, we can have more than one imaginary number. And so what is this? This is a square with an area of -2, or a square with an area of -3. And then of course you can go on and on and on, because I can now add some other number to this, right? That's then called a complex number. Any number that is in this form, a plus bi, is referred to as a complex number. This component is the imaginary number. This component is the real number, and they are both terms in the negation problem. B is real, A is real, and I is the imaginary number. Right? For real numbers, we have a number line, okay? And every point on that line represents a real number, right? Starting with 0 in the middle, we have positive numbers over here, the negative numbers over here. In between 0 and 1, there's a whole infinite number of real numbers in there. I mean, it's just every real number has a dot. Imaginary numbers don't have dots. These are actually two-dimensional numbers. The real component of the number is over here, and the imaginary component of the number is on the y-axis. Okay, so what does that mean? That means that right here, 1, 2, 3, 4, this is how many eyes you have. And over here is how many ones you have, okay, or real, you know, your quantity in real numbers. And you can have an infinite number of eyes here. I mean, you can have half an eye or 3/4 of an eye or whatever. And if I put a number over here, we represent this as, let's see, it's got 3 eyes and 3 whole numbers. So it would be 3 plus 3i. And this together is a complex number. Right? This is not 2 coordinates. It represents a number, just like the points on a number line, but this represents a complex number. So these are complex numbers on a complex plane. Okay, and they are all represented as a plus bi, where a and b are real numbers and I is the imaginary number. This actually ties in with what we've been doing, because if you go back to this for a minute, we started out saying, okay, if I give you a point out here and I tell you that the terminal side of an angle goes through that point, what is the measure of the angle? And we learned how to do that last semester. And then I said, okay, so here's polar coordinates, right? Where we're going to, instead of calling this by a rectangle, we're going to call it by an angle and a distance. Okay? And we were able to do that. Okay. And then the next question became, wait a minute, can we do the same thing with this? Can we represent complex numbers with polar coordinates? And the answer is yes. We can take this thing here and represent it in a polar fashion. Now, it's not polar coordinates, right? Because polar coordinates, right? This was x comma y. That was rectangular coordinates. And then we decided that the same point could be called r comma theta. But this is not x comma y. This is, you know, a plus bi. So how are we going to do that here? Well, the answer is we're still going to use this distance and call it r. And we're going to use this angle and call it theta. But a plus bi can be represented as r times the cosine of theta plus r times the I times the sine of theta. Okay. And if you look at that, you say, well, wait a minute. Yeah, I guess that makes sense because r cosine theta is the a coordinate, right? The x coordinate here. And r sine of theta is the y coordinate. And then if I multiply that by I, that's exactly what this is, a plus bi. Our book does this. In typical mathematician fashion, it says, this is too much to have to write. I'm too lazy to do this. Here's what I'm going to do instead. Right? I can factor out the r, and I'm going to use c for cosine, I for the imaginary number, s for sine, and I'm going to put a theta in there, and this is going to be r cis theta. And that is exactly the same as this, only written shorter. The fact is, I have not seen this anywhere but in this book, but I love the idea because it means you don't really have to write it all out. Okay. So that's pretty much all I have to say about this, because all of the mechanism for switching complex numbers in rectangular form to complex numbers in polar form is stuff you already know how to do.